Okay, so we're going to talk about what Hamiltonian do I have to add in a quantum system describing an atom or a molecule if that quantum system is interacting with a monochromatic electromagnetic wave. And so in the picture, what I've shown is our atom or molecule, and then along comes the electromagnetic wave. And here we're just assuming that you have a fixed wavelength and a single frequency. And so we have electric and magnetic fields that we can write as E for the electric field. That's going to be some fixed vector that shows the direction and the magnitude of our electromagnetic field. So this is going to be some linearly polarized wave. And then the space and time dependence would be a sinusoidal function that I'm going to write as cosine k dot x minus omega t. And k is a vector in the direction that the wave is moving, and the length of the vector is inversely proportional to the wavelength. And then omega is going to be the frequency of the wave. And for light, the omega is just going to be the same as the magnitude of k, okay, because the frequency and the wavelength are related for light. Okay, so that's the electric field, and then there's some perpendicular magnetic field. So B is going to be equal to, so let's say E0 would be a vector that shows which direction the electric field is in. Now B is going to be always perpendicular to that if we have an electromagnetic wave in the vacuum, and it's also sinusoidal with the same K and the same frequency. Okay, and the length of B is related to the length of E. I think you just divide the magnitude of the electric field by the speed of light. So you can review the electromagnetic description of a monochromatic light wave, but these are basically going to be your electric and magnetic fields. Okay, and so now I assume that you've watched the video about writing down the Hamiltonian for a charged particle in an electromagnetic field, and so the result of that video was this general expression for the Hamiltonian. And that's expressed not in terms of the electric and magnetic fields, but in terms of the vector potential and the scalar potential that we can also use to describe those same fields. And so in order to get these particular electric and magnetic fields, one choice of vector potential and scalar potential that we can choose is the following. So you can just check that if you plug these in to the formulas in the previous video that relate the potentials to the fields, then you get the expressions above. So we can actually take the scalar potential to be 0, and we could take the vector potential to be minus 1 over omega times E0 times sine of k dot x minus omega t. So you can check that, just plug those into the formulas for the electric and magnetic fields in terms of the potentials, and you should get the results up here. Okay, now, so in principle we're done. We just use this form for the vector potential and that form for the scalar potential and plug that into the Hamiltonian above. Okay, but we're actually going to simplify things by making an approximation that is often valid when we're talking about atomic and molecular systems interacting with electromagnetic radiation. And so the approximation stems from the fact that actually, unlike the picture that I've drawn above here, it's often the case that the wavelength is much, much longer than the size of the atom. Okay, and so let's think about that. So the atomic size, we're talking about something like 10 to the minus 10 meters. And if you think about, say, ordinary light, so what is the wavelength for ordinary light? So that's something like 500 nanometers, or 5 times 10 to the minus 7 meters. Okay, and so that means that unlike that picture above, really if we have our atom, okay, say it's a hydrogen atom, and the typical size of that would be an angstrom, then the wavelength for our light is going to be 5,000 times larger than that size. And so really, if you're that atom, you're not really seeing the spatial dependence of the electromagnetic wave. You see some very slow, so I can't even draw that, but so here's a very long wavelength wave compared to the size of that atom. And so mainly what you would see is just a spatially constant electric field that's oscillating up and down with time. And similarly, a spatially constant magnetic field that's oscillating back and forth with time. Okay, so we can take that into account mathematically. What does it mean for our formulas? It means that K, which is, remember, that's inversely proportional to the wavelength. It's 2 pi divided by the wavelength of our radiation. If we have K dotted with X, which is the thing that shows up in our formula there, for the typical positions that the electron or the other charged particles in your atom or molecule are going to be in, we can take that to be very small. Okay, and so if we use that approximation, then, well, we still have phi equals 0, but now we can approximate A as minus 1 over omega E0, and then just sine of minus omega t. So we're saying that the k dot x term in that expression for all the likely positions of your electron in your molecule is going to be very, very small, and so we're just going to ignore it compared to the omega t term. Okay. Now, after we've done that approximation, we can actually now make an even simpler choice for the scalar and the vector potential. So we talked last time about how I can do a gauge transformation. It's just a transformation of phi and A that gives me another choice of phi and A with the same electric and magnetic fields. And so I'm going to do that now. So we'll simplify the whole problem by a gauge transformation. Okay, so this is just a mathematical transformation where I take phi goes to phi minus the time derivative of some function lambda that I will tell you, and A goes to A minus the gradient of that same function lambda. And we are going to take lambda equals this constant vector E dotted with X over omega times sine omega t. And so the point of this is that for any transformation like this, this represents a change in the potentials that doesn't change the fields. And now we're just making a particular choice of that. And the reason is that after we make that choice, then we find that phi nu, now the phi is not 0, it's equal to minus E0 dotted with X times cos of omega t. And the A after our gauge transformation is basically 0 within the approximation that we were making above. Okay, so really the A has small terms that we ignored. And if you want to very accurately or precisely solve this problem of what is the effect of this electromagnetic field on the atom or the molecule, then you'll eventually need to take those into account. But in many circumstances, it's fine to ignore them. Okay, and so now we're all ready to write down our Hamiltonian, and it's very simple because we just ignored that term and ignored that term now because the A is very small. And so the entire term that we have to add to take into account the effects of the electromagnetic field is just this last term. Okay. And so we find that for basically each charged particle in our atom or in our molecule, we have to add a term HEM is equal to minus. So we're just plugging in this guy into here. And so we have HEM equals minus Q times E0 dot X times cos omega t. And we have that term for each charged particle. So if we had several electrons in a molecule, we would be adding that term for each of those electrons, for example. And so the total thing that we have to add, so the total H prime of t, in this approximation, it looks like minus the sum over I of your various charged particles, Qi, and then we have the position operator for that ith charged particle. All of that's dotted into our vector E0 that tells us the direction of our electric field. And then we have cos of omega t. Okay, and now this operator has a very nice physical interpretation. This is precisely the dipole moment operator. Okay, so this operator defines what's called the dipole moment of our molecule. It's just a sum over the various charges, and it's the charge multiplied by the position operator. Okay, so for example, let me just remind you, if you had a plus charge here and a minus charge there, then the dipole moment ends up being some vector which is in the direction from minus to plus, and so you can work that out. For example, if we define 0 to be the location of the minus charge, and then our vector is just going to point towards the plus charge, and the length of that vector is going to be p, and that will be equal to q. So if this is plus q minus q, and times r. Okay. So the Hamiltonian that we have to add is the dipole moment operator for our molecule, dotted with this electric field direction, and then times the sinusoidal time dependence. Okay. And so in the next video, we're going to use that with time-dependent perturbation theory to actually figure out the transition probabilities for spontaneous emission or absorption in atomic or molecular systems.